Now we will have Vivek Borkar telling us about the
Thank the organizers for the invitation, which was also a pleasant surprise because I don't really work in the CE with details. But then I conjectured that I had one of word long study stochastic approximation with it was long range dependent and limited. And that was motivated by something else. When communications pointed out that all the algorithms assume uncorrelated noise and nice movement bounds, but in reality they are both long range dependent and deviated. So we tried to stretch the existing theory to at least some special scenario where both these problems are there. But before doing that, I'm actually going to sort of tutorial on a particular approach, the stochastic approximation based on ordinary differential equations. There were revisions to that, but it's quite well developed, particularly among people from control and communications. And it has its own kind of bag of tricks. And I felt the flavor of the results we look for are typically almost sure and so on pathways when concentration bounds are operated and high probability rather than expectation. And nevertheless, I think it might find uses in, I mean, I'm sure it's being used already in some subculture within the ML community, but also a whole more. So I refer to bullets as essentially that, and then we stretch it to deviated noise, which is somewhat routine. Let me do a quick survey of the stochastic approximation version. It is the Robinson Monroe long ago, 1951, if I recall, and that's that iteration xn plus 1 is xn plus kn times hxn plus mn plus 1. So the term in bracket is a noisy measurement of h. So given xn, you just get that sum. You don't have hxn and plus 1 together. And the clever thing they did was to impose this slowly decreasing step size. Namely, sum of n is infinite, sum of n square is finite, and there are some textbook examples which are actually not terribly useful. If you implement it, they become very small, very fast. So what one really does is a 1 by n with half for 1,000 steps. That and that was fun. There's the province with a wife when he was in Navy. So I'll make some standard assumptions. HV left shifts. Mn is assumed to be a martingale difference noise. It means that correlated with the past in the sense that one step conditional expectation of each component given everything you know up to n as captured by the sigma script fn. It's 0. And furthermore, I'll impose this kind of conditional moment bound. And that plays an important role in what we'll say later. So, if in particular the iterations do not blow, that's not free. You have to justify it. But if the iterations do not blow, then this condition implies that the second movement of the martingale difference sequence is also uniformly bounded. And that helps. This one thing I want to be clear is that it is more general than it appears. It appears like additive martingale difference noise, but generic algorithm will look like this: f of xn comma xn plus 1, where xn is IID. Say, just add and subtract one step conditional expectation and it reduces to the additive martingale difference. So it is quite broad framework. For example, in reinforcement learning, this is what we do. We add and subtract conditional expectation and it fits the just whatever hx is just one step conditional expectation. You add and subtract hx, you get the original noise xn comma xn plus 1 is hx plus n. And the numerical approach of Robinson based on some, it was probabilistic and the results were also weak. If I recall, the Robinson Monroe was convergence in probability. Later on, he himself, Sigmund and Robbins had this extension of supermartingale convergence from non-negative supermartingale. They use that effectively, and even now probabilistic proofs use variants of this, but I will go for the ODE approach for ordinary differential equation, which has roots in Russian, Russian research in mid-70s, which was actually developed significantly by Leonard Lyon, and then a lot of other developments. Finally, in 1996, Benham gave a very general, clean treatment of the general scheme without just a characterization of a general attract. Okay, so let me just motivate that. So if you have x naught t equal to h of xt, that's the kind of target ODE you expect to track. Then think of the Euler scheme, which will be xn plus some small steps as a times hxn. So you can think of stochastic approximation. The difference here is that A is replaced by A in here, and there's this additive noise. So it's basically a noisy Euler scheme with a slowly decreasing. So you do expect it to track the ODE. And the Robins-Monroe conditions, and in hindsight, given the ODE interpretation, you want to track the asymptotic behavior of the ODE. So some n being infinite, make sure that you actually cover the whole time axis. Sum of n square being finite, say that n is going to 0 in particular. So the approximation gets better with time. So yes, so n going to 0 ensures that discretization error is going to 0. For that, you don't need the square summability, but square summability also ensures that the error due to Martingale noise is going to 0. Because you are multiplying the Martingale difference by n, so you scale it down the additional variance by n square. So, and to pass the started late, so a bit panic.
Yeah.
Okay, so this is a sketch of the convergence analysis. Anyway, I want to make some comments based on my first exposure to the machine learning HGD. So, already found out what maybe that's one thing. Yeah, so the iteration, let's go back to our iteration. And then the way to think of it is that A is a time step. I'm thinking of it as a time discretization. So let's start with T0 is 0, T1 is A1, T2 is, sorry, T1 is A0, T2 is A0 plus A1 and so on. So I define the discrete time steps. I call that the algorithm time scale. And then I define piecewise linear function, linear continuous function x bar t that coincides with xn at Cn. Xn at n and interpolate linearly. So just the definition. It's both continuous and piecewise linear. And I'll assume, so this, as I said, is the non-trivial assumption for stability. So assume that the iterates remain bounded. And then the idea is that you fix capital T and take a moving window T2, T plus capital T. If you compare from time 0 forever, the errors are going to wait that. So you can take a moving window and compare it with your trajectory. So I take this window T comma T plus capital T and compare it with this ODE trajectory x sub T S for L belongs to T comma T plus T. So the superscript will denote the initial state. And this is the picture. You keep moving this window, and then what you find is that you reinitiate, so that jagged curve is the piecewise linear interpolation, and the colored things are ODE trajectories initiated at the same initial point, and they get closer and closer as you shift the window to the right. I'll just sketch the proof. So we will skip the content. So you can consider some t n plus k, the difference between x bar and x sub t n at the same point, and you just as a standard sort of triangle inequality will do something like this, where 1 and 2 are not yet specified. The 1 I call the discretization error, and 2 is the error due to noise. Okay, so this is one more step. Let's do the Lipschitz condition. So the difference between here I have h. I get rid of h and replace it by x bar and htn by pulling out Lipschitz constant. And then this 1 and 2 are errors to be specified. Then just discrete don't want inequality for constant dependent factor to type the 2 errors. So if I show that the errors go to 0, that will tell me that this to directly approach each other. Now the error due to discretization ends up being basically bounded with some constant times sum of am square m from n onwards. So since that is square summable, it goes to 0. This is easy to show that error 1 goes to 0. In fact, it kind of overkill it, otherwise show more easily that the square summability is not essential, but we don't have it anyway, so might as well use it. It is crucial for the martingale error. So if I consider total noise, so zeta n is total noise from 0 to n, which is sum of m of n plus 1. These are martingale because m was martingale difference sequence, so I weighted sum. And then what I have is the sum of conditional second movements. I get this part using the bound I had put on conditional movement of the martingale difference and my assumption that the iterates are bounded almost surely. And this by convergence, martingale convergence theorem tells you that zeta m converges, and our error due to the martingale difference noise is that part of the tail of a convergent sequence, so that also goes to 0. Oh, sure. So you have actually on this moving windows, the two approach each other. Now the claim is that if the set of limit points of xn and then goes to infinity, of course everything I say is almost sure, I didn't say mention that way. Then it converges to an invariant set of the differential equation. I think the picture is better for the words. So suppose xn goes to some limit x star, okay, and consider that the trajectory of time duration capital T starting at xn. Basically, by continuous dependence of differential equations on initial condition, it will converge to the corresponding trajectory here. But you want that interpolated trajectory to converge, but these two are approaching each other with time. So the dispatches of the interpolated trajectory also converge to the leading trajectory. So this tells you that the trajectory started at x star in forward time will remain within that set. So this set of limit points. Repeat argument in backward time, you get the negative invariance as well. So it's very so this is actually some diagram now in the picture. Yeah. So when I take this the definition, so this terminology called internally chained transitive invariant set. This comes introduced by a person called Conley in dynamical systems theory. So what it says is the following. So this is an invariant set. What it says is that I am given 2 points. This, then given any epsilon positive and capital T positive, I can find a finite collection of points there. So that I have a collection of trajectories starting within epsilon of this point and reach the epsilon equal of the next point after atom time t greater than equal to capital T, which I use basically. And you can do that and then finally reach epsilon level. You can go from anywhere to anywhere modulo with the small jumps with trajectories of prescribed minimal duration. So what when I show that xn converges to an almost surely converges to an internally chained transitive invariant set of the differential equation with the most general characterization of limit sets of stochastic approximation. So of course we are interested in algorithms you want to find, yeah, but we are not always lucky to just confine yourself to it. Of course, gradient descent only equilibrium, but there are even in machine learning, like reinforcement learning, very often fx is of the form fx minus x. You are looking for this point of some hot action or non-expansive map, and then it may not be a equilibrium. In particular, multi-agent reinforcement learning, you do run into this problem. Yeah.
So duration at least t.
Yeah.
So longer than t.
Sometime after t.
After t.
If you don't put that, you can sort of trivialize the definition by taking some arguments.
All right.
Okay, so this is the one thing I want to say. I said that I assume that this threshold law and there's no universal. There's one stability test and mentioned, which was useful certainly in reinforcement learning. Basically, it assumes that this limit h infinity x, you just scale it, h multiply x by c and divide h x by c and let c go to infinity. Assume that limit exists. Basically, what it means that the dominant term is linear, with the dominant linear root term, which is true for dynamic program, which I got described useful in IO. And if that ODE has, it's argue that one homogeneous would definitely have origin as an equilibrium, positively homogeneous, and then the claim is that if origin is the only unique globally perfectly stable equilibrium, then the iteration is not there. And the intuition is later on, depending on the time, I'll mention the counterpart we have for the Vivek case. The intuition is similar there, but here it's easy to display. So the thing is that what so if that you compare again, take moving windows, rescale the trajectory so that at initial point, if it is within the unit wall, leave it alone. If it's not, the rescale it so that the norm is rescale it by the norm of the initial condition on that patch, so that it starts on the unit wall, and look at these rescale trajectories. Now, if the original patches are blowing up, then the rescale patches will start approximating x dot equal to infinity. If you are scaling it by something which is going to infinity. So if this is coming back to the origin, these patches have to come back to the origin. And they differ from the original iterate just by a scaling factor. So the original iterates also have to start coming back to the origin. So there is the stability test. One of the stability tests is useful, but there are other stability tests also. I don't think there's any universal test for that always works. Then there are some minor extensions. Then you can add this. This is sometimes because of this approximate gradients and so on, which kind of things come up. There may be some small adapted non-noise error which either asymptotically goes to zero or is small. If it asymptotically goes to zero, no problem. Same analysis will handle it. Otherwise, you can claim only wherever I claim convergence, you can claim convergence to a small level. And you can also have adapted state sizes. So AN can be adapted, but then of course that's variable. It can be random, and this happens, for example, in distributed multi-agent setting. Because if you are distributed asynchronous as well, so if you are adapting, if you are updating only one or components at each time, then you have to consider separate clocks for each component, and that should. Okay. So this is a joint paper with Anantharam. Okay. Appeared in, so this is predates the machine learning. So it was published in 2012 or even done in 2010. So it's a kind of academic exercise. It doesn't look at the same kind of issues that. So what I have done is, okay, the zeta n plus 1 is this harmless term which will go to 0, but the n Sn plus 1 is something extra, where Sn plus 1 is an increment of an first item process with a for so zeta n is harmless. So actually the paper also has an additional term involving actual problem emotion, and that was a lot more problematic than because and we don't have martingale increment, and that's here from martingale. Yeah, so the DN is some again adapted to this. So DN is just that multiplying the increment. Again, we have to make it a little more strict. Order 10 to the minus kappa, which is half and 1. And this satisfies the Robinson-Monroe condition certainly. And we also assume that we consider kind of convergent case that actually x dot equal to HT as a unique probably symptotic stability. So then you know that this by conversely Lyapunov function, we only need the existence. Let's take this Lyapunov function, which goes up to infinity and now it's going to infinity and the other out away from extra v dot h is strictly negative. And the claim is that for some psi, if I assume that for some psi this moment is bound psi between 1 and alpha. So alpha was strictly between 1 and 2. If this movement is bounded, then for any smaller psi prime, you get convergence in convergence is psi prime to double shoot. And this condition, this dagger, replaces the I had this almost sure stability condition assumption earlier for the vanilla case that supremum norm extend the bounded surely. So this uniform movement bound replaces. So again, you start by comparing the ODE trajectories. So I use the same notation for constants of right now I have called it KT minus C. So basically the same idea. You discrete normal inequality to get something like that. So there are two extra terms, but this is the minor term. This is the real nuisance. And the claim, the main thing to prove is that this phenomenon was the supremum over that window set movement close to 0. Or should have decided. And what the scaling property to do this discovered the publication which is around just a few years before us. We started on this for maximal inequality of level stochastic integrals. So we read this sum of Tn S n plus minus Sn as the stochastic integral of this is constant time process. So that there is what that Weber has much more level, but for us it reduces to this. So this is true only for x large enough. And then given our assumption from the choice of alpha, etc., we can show that this term epsilon n from alpha is bigger than 1. And then okay, I'm not sure if we're going to do this, but basically it's in staggered calculations. At some point we plug in the. You see, the reason you do this is that this inequality holds true for x bigger than this. So if you split this integral into parts, basically the bound and separately. And here the second term she's talked about the test also. Just that I'm using the same number, it's about C for the combined constant. So it's the kind of standard probability. And that goes to 0. So that also basically helps us. And to conclude the proof, I think later on we realized we could also use this, but this gives the thing is we kind of left it at the asymptotic result, but we can probably do more. Because classical case you can do a lot with but not just the for example, concentration bounds and distributed intermediates with delay and so on. So we have okay, so further then what is the common moment for everybody? Every term I do the same with martingale difference. Substandard martingale inequality for martingales and bounded by the side power of this thing bounded by psi by 2 power of its particle equations. So using that, again, I'm able to show that this part of it, which is the this is the trivial anyway. So if we get what we want that uniform. The more we do, you will in the C can be replaced by T. Then this X, so X NT was the OD starting at N, and without loss of take any initial time as disposition. And that the rest of the argument again is different because it's not almost sure, but it's inspired by what we do in our perspective. If you look at, you want to show that this goes to 0. If you truncate it at some large enough L. So let's look at this last term. So this term I can make small by say x1 by 2. Third term by making n large enough. So that's not this one. Here what I have done is to split this x bar minus x star into x bar minus xs and xs minus x star. And second term can become small for s large enough because I know that on the moving axis the two approach each other. And here I pick capital T large enough so that any trajectory starting within n ball will come within epsilon by 2 of x star time capital T. Using the asymptotic stability of x star, I know that it start with ball of fixed ball. There's a uniform time capital T, so if I start within the ball, after time T, I will be within. So just put all of them together, then you get emergence in separate. And yes, so I'll probably go to this somewhat. So basically here again, I add up the stability test for this case. So here again, I assume very different. But yeah, I mentioned that before. Yeah, I forgot to mention this convergence. Convergence for free is uniform on compact space because they all have a combination. Here, what I do is to normalize instead of sample pathwise, I normalize because with linear interpolation. Then you consider the corresponding basically rescaled positions and you have this kind of convergence. And by construction, this remains bounded because I have rescaled initial condition the rescaled and norm one. Again, the same argument. Suppose around some subsequent they were going up. Then by using the discrete, you can go over inequality the other way. Basically, if this goes up, it has to go up uniformly on that patch. It cannot just go up on the initial condition. And then pick capacity large enough so that the ODE start it was ODE at infinity. I think would be within 1/8 of its initial condition for t greater than equal to 6. And then basically you mimic the argument for the pathwise case. So once this C is large enough, this is the C was the normalizing factor, which was the norm for the value of norm moment. So if C is if it's blowing up, C will become large enough that this will differ. And basically that means it same kind of argument. You have to just an approximation argument. If the ODE at infinity has to start coming down, then the ODE close to infinity, the C large enough has to start coming down. And since this trajectory approximate that they have also the rescaled trajectory approximate that, they also have to start coming down by a certain factor. And since they differ from the original trajectory just by a scaling factor, so I'm taking because of that, and that reason I'm taking a multiplicative kind of thing. Normal condition divided time divided by no initial time is less than equal to 1/4. So that doesn't change if you change the scale. And therefore, just to show that it remains. Yeah, so the details are a little more complicated and what I bring this out. So there's almost all the end. But the stage is so actually the classical stochastic approximation community looks at slowly decreasing step sizes. People do use constant step sizes, particularly in signal processing, where you are trying to track a slowly varying environment typically. And if you see the decreasing steps, the algorithm moves slower than the environment and you cannot track the standard constant step size, but then the results become deeper. Wherever I say almost sure convergence, you can say that if the step size is small a, it will be some, you concentrate high priority in order age where you cannot say bounds. Then there are finite time bounds. Okay, there are again high priority bounds. Okay, there's another thing that 2 time scale is something with including the you can, I think you are asking when you can have different component and different step sizes, inducing different time scales. And that can evaluate various rate averaging and so on. For example, in actor critic, you can do the actor learning on a faster time scale, critic learning on a faster time scale, and actor actually does the optimization on a slower time scale and so on. And there are many other cases where you can do that. And in fact, you can treat to what did was to share this Markov chain in the background. So that works on what I call the natural text, that n equal to 0, 1, 2, 3. So when you are running your algorithm on a slower time scale, between n which is going to 0, it's already a 2 time scale effect. So the expected value of the retreat, the function of your retreat will actually track the statistics. So if you are interested, definitely the asymptotics you can go without having to do any math. I don't know about the concentration bounds whether they will be equal or not, but certainly asymptotics and for the also the concentration bound we look for high probabilities. I don't know whether not exactly right. Then the distributed asymptotic implementation, of course, because of asynchrony, instead of x dot t equal to sxt, you get dot t equals to lambda t the diagonal matrix. So this positive integrates, negative integrates, they reflect the relative frequencies which you are sampling different. For certain cases like gradient descent and say infinity contraction, infinity non-contractions we happen in dynamic programs, as long as they remove the diagonal entries are bounded away from 0, you can get them. So we use the convergence rate. This is not something frequently a sequence case, but you get the same convergence rate. And there are other ways in other cases when you cannot prove convergence, there's a way of tweaking. If you need some additional condition on the step size, and if you use a local clock, so I using an, it is a of new I comma n, where new I comma n is the number of iterate the ith agent till time n. Then there are suitable conditions on an, you can show that it doesn't matter. The average tends kind of the average weight given to different components balances. Correct. So what is what I want to say, and I want to point out what I conclude. A lot of this discussion of flat minima, etc., reminded me of one result which I pointed out already to a couple of people, but Anand is one of them. And Murthy was here with me. So there's a paper by Chure Wang in Annals of Probability 1980, which looks at the distributions of the type. It certainly will work for basically Lagrange type of thing. If you e to the minus v by epsilon square normalized, okay, then as epsilon goes to 0, it concentrates on the global minima, and the weight is proportional to square root inverse of determinant of the ratio. The one way to motivate is that near, suppose x0 is one of the local minimum, you look at Vx in the, is concentrating at local minima. You look at second order Taylor expansion, Vx0, it cancels in the numerator and the denominator, which is the partition option, plus some term involving grad Vx0, which is 0, because it's a local minimum, and you get half x minus x0 transpose, Hessian Vx0, x minus x0 transpose. So after normalization, it will be like a Gaussian with Hessian inverse of the covariance matrix, and the normalization to make it a probability distribution, asymptotically become a Dirac there, involves basically square root of determinant. So it puts weight, it just puts the weights proportional to square root inverse of determinant at that point. I was wondering if I'm not familiar with what all is known about KV tails, but if you can put the stationary distribution as e to the minus h by epsilon plus a small lower order terms, then this should help. In particular, I think even in the non-gradient case, I have not seen it, but it should be easy to do. In the non-gradient case for diffusions also, you know that it concentrates on the minimum of the Fresnel that was the potential. There also the counterpart should be true.